Hello students, my name is Shashank Shekhar. So in the previous class we have started something about atomic model. We have seen the Thomson pudding model and all. Now what we have key things that okay, the Thomson pudding model was good. It was able to account the electron neutrality, but later on experiment came, that was Rutherford's experiment, that scattered this kind of uh, atomic model, and Rutherford put his new model there. Now let us move to that thing. So these were the conclusions that we got. Okay, that the charge on the electron is this much, the charge on proton is this much, and charge on neutron is this much. But here if you see that in the previous experiment that we have conducted lastly, that we have seen lastly, was our say this canal rod tube, or you can say electron discharge experiment and all. So through tube we passed a kind of electricity, high voltage electricity, and then we saw that okay, we are able to measure the charge is to mass ratio. Okay, but we didn't measure the charge. So here the charge is mentioned, and that charge was calculated by Millikan with his famous Millikan's oil drop experiment. So first we'll see that experiment, that what is Millikan's oil drop experiment, and that is very fantasizing to see. Okay, so this is the experiment that is being done by the Millikan. If you look at the right side, you will see a image there, and atomizer is written there. Something called atomizer is written there. You can think it of a spray. Now, that spray is connected with the source containing oils. Oil is there in the source. Clear? Now, what is done by the atomizer? This atomizer is taking the taking the oil from the container and spraying it in the chamber. So this is the chamber that we have. Now in the chamber we have a setup. The setup it is in this way. Okay, there is a blue plate here that is positively charged. There is a kind of orange plate in the downward side that is negatively charged. Now here on the left hand side we have a telescope. On the right hand side we have X-ray. So what is this X-ray doing? So basically what are we doing is we are passing this oil drop with this kind of hole that is present on the blue plate. Now as this oil drop is falling down, now with the help of telescope, what we are doing, the downward motion of the droplet is observed, and by measuring the rate of fall we are determining its mass using the simple Newtonian mechanics. Okay, so what are we doing? We are spraying oil here, and that oil is getting accumulated on the top of the blue plate, and on the blue plate we have a small hole in the middle through which the oil is dropping, or you can say it is leaking, and it is dropping through that hole. And with the help of the telescope we are observing this oil drop and measuring the retarding. With the help of their motion we are measuring the mass of the oil drop. Clear? Because height and all is unknown, so we can easily calculate the mass of the oil drop. Now once we know the mass that is being flowing through this drop, through this hole, in the next step what we do is the oil drop is continuously dropping. Okay, this is the one thing that is happening. Now the second thing we do is that we pass the X-ray. So on the right side you can see, on the opposite side of the telescope you can see that we are passing X-ray. Now this X-ray is doing what? It is ionizing the air that is between these plates. Okay, did you get that point? So what are we doing? So with the help of X-ray what are we doing? We are ionizing all the air. Ionizing means we are taking out the electrons out of the gaseous atoms and making it a ion. Clear? And why it is happening? Because of course X-ray is electromagnetic radiation. Electromagnetic radiation is a form of energy. So with that energy we are ionizing the air that is present between the plates. Okay, now what will happen? There will be a kind of gathering of charge between these plates. Now this charge or this ions will interact with the oil drop. Okay, that will interact with the oil drop, and in that process our oil drop will also will also be charged. Okay, you can easily think of it that why it is getting charged, because it is interacting with a charged particle. For that reason it must be getting polarized. Okay, the electrons and protons must be accumulating on one side, on the opposite sides, and that is the reason they are getting what? They are getting charged. Now, since this oil drop is charged, now you can think of it that okay, we are between the electrode potential. Okay, we are between a potential in which a positive and negative potential is applied. Now it will of course affect that oil drop also. The movement of the oil drop will be affected because now it is charged because of the collision with the gaseous atom that was gaseous ionic atoms that were present here and there. Clear? Now if we carefully balance this kind of electrode potential, then either we can retard the speed of the falling oil drop, or we can accelerate it, right? Or we can make it stationary also. So that is also possible, right? So we can do these three things. Okay, clear? Now this all this retarding and accelerating will depend upon the first thing, that is the charge or the polarity that has been developed in the oil drop, and second, the voltage we have applied on it. Now by carefully measuring this electric field and the motion of the oil, we have calculated the charge, okay, the magnitude of the charge on the oil droplets. And this is always, so we have done it multiple times for multiple oil drops, and we found that this charge is always an integral multiple of a E. Okay, so what I'm saying is that, so what we did, so first we took an atomizer, or you can simply think of a spray. We are spraying oil droplets. Now this oil droplets is passing through the hole. Initially we don't have ionized air, okay, ionized air, and now by viewing it through the telescope, we are able to say calculate its mass and all with the help of simple Newtonian mechanics. In the second step, we passed X-ray, make the make the air ionized that is present between the potential, and due to that ionized air, that ionized ions collide with the gas oil particle and make it polar, right? Now it is being charged. Now this charged oil particle under the influence of the potential can be retarded, means it can be made to fall slow, it can be made to fall fast, or it can be made stationary also. So these three things can be done, and with the help of that, how it is reacting to this electrode potential, we calculated the charge on that oil drop, and it was found that each time we calculated the charge on the oil drop, it was always a integral multiple of E, and that E was considered as the basic fundamental. Okay, that is the basic fundamental, and n can be 1 2 3 or 4 either, right? So that in this way we are calculating E here, right? Okay, and that is the charge on the electron that we have. So in this way Milkins was able to calculate the charge on the electron. Clear? So why is it so that it is always an integral multiple of E? Because see, charge most fundamental means the most fundamental particle of charge is E, that is your electron. So if every time you will have the charge, that will be always an integral multiple of E. You can think of it in this way. Suppose you are just taking a cube, right? You are taking a cube and you are filling it with a stone, okay, with various stone, and all those stones are of same dimension, suppose, and those stones are suppose cubic in nature. So you are taking a cube, filling it with stones that are cubic in nature, and now you are filling it until it gets completely packed. So we are taking the ideal condition that okay, the cubes that we have taken are such that they are identical and they are completely filling that cube, means no space is remaining. So you can think of it, just visualize it. Now suppose I have taken 10 such cubes, okay, I have taken 10 such cubes. Now if you just multiply, if you just calculate the surface area of whole of the cube, right? If you just calculate the surface area of the whole cube, and you know that okay, we have 10 such particles, right? Now you can just multiply with n, okay, the 10 into n, and n is the volume of one cube and is equals to the volume of the whole cube. Now if you calculate the n, then you can get the dimension of that cube, right? Clear? Similarly here we are doing the same thing, okay, but instead of that we know the overall charge, okay, we know the overall charge. Of course, we don't know n here because the number of cubes is not known. So for that, you will take several experimental, several you can say observations, and you can just equate two of them. Okay, you can just equate two of them and see that whether what is the value of n, and then further you can calculate the value of e once you get the n. Clear? So in this way, so in the cube case, we know that that small cube that we have taken was the fundamental thing. Here also, the electron that we have taken is the fundamental thing here. Clear? Okay. So this is about the way we can calculate the charge on the what? Charge on your electron. Clear? So this was the Thomson model. Okay, this was good. Okay, we know that okay, it deals with the charge neutrality and all, but the difficulty came when it was inconsistent with the experimental data, right? And that difficulty was mainly challenging that okay, the mass was uniformly distributed and this thing was disrupted by the Rutherford model. Clear? So before moving to the Rutherford model, we should know some terms. So first of all, we will know about some alpha, beta and gamma rays. So what are alpha, beta and gamma rays? We will know them. So certain elements emit radiation on their own, and it was discovered by Henry Becquerel. So radioactive compounds are those which emit particles that are very unstable kind of thing, and they are very high in energy, right? And these are emitted by various elements like you the most common is uranium is radioactive in nature. They continuously what they do? They emit neutron and proton, right? They continuously emit neutron because their nucleus is getting decayed, and that nucleus is very high in energy, and that interact with other particle and make other particle ionize. So you can think of the same way we are ionizing the oil drop, but that neutron is since having the high energy, it can break down the nucleus of other element. Clear? Okay. Now coming back to this rays that we are emitting. So it can be a neutron, it can be alpha particle, beta particle, gamma particle. Now you will use this alpha particle. That is the reason I am getting into it. So what is alpha particle first of all? Clear? So if you consider alpha particle, it is simply high energy particle with 2 units of positive charge and 4 units of mass. That is your helium nuclei. Okay, because helium has a atomic mass of 4, so it is a helium nuclei. Now helium gas is yielded when combined with 2 electrons. Okay, so alpha particle is He2 plus. Okay, what is helium alpha particle? Alpha particle is basically He2 plus. We are removing 2 electrons, and now only 2 protons are there. That is making it making it charged, having a charge of 2 plus, and since there are 4 neutrons present there already, we know that the mass of the helium atom is 4. So it has a mass of 4 unit and it has a charge of 2 unit. Clear? So it is basically He2 plus ion. So that is called as alpha rays. Clear? So this basic thing should be always in your mind that okay, what is alpha particle? Alpha particle is helium, nothing but helium 2 plus. Next is beta particle. Now beta particle is similar to electron as it is negatively charged. It is simply electron, right? Then it is gamma particle. So gamma particle is the most you can say very destructive thing that has very high impact, disastrous impact on anything that it interacts with. Now it has no mass. Okay, it has no mass. It is just high energy radiation. Okay, it is just like high energy radiation. As we have seen, X-rays, right? X-rays were very, if you just put it with very high energy, it can ionize the atoms that are present there. Now, this word ionization is heard by you various times, but believe me that this ionization is a very difficult process. To ionize something, to take out electron of something is a very difficult process. It requires a large amount of energy. And if some rays is capable of doing so, then it must be having a very high amount of energy. Clear? Now, this gamma rays are also what? They are having no mass, and that makes it dangerous. Okay, it has no mass, so it makes it dangerous, and it can easily penetrate through anything. Okay, I mean anything, it can penetrate through anything because it does not interact with the particles. it goes between the particles, right? Because it has no mass at all. It is just rays, right? It is just rays. So it never interacts between the particle. It just goes and penetrate anything. So it has the highest penetrating power. The least penetrating power is uh, held by alpha, and beta is in the middle. Clear? Okay. Now let us move to alpha particle scattering. So that is the reason I have started with alpha particle. So what we do here in the Rutherford experiment, we take a gold foil, a very thin gold foil, and we bombard, or we just throw alpha particles on that gold foil. Now, when we do this, we have various observations. So this is the experimental setup. Now here is the source of alpha particle. Here is a lead plate that is just making it singular, and now here is a gold foil. Now that the gold foil is bombarded with this kind of alpha particle, now this some of the alpha particle, what happens? Some of the alpha particles went straight through. Okay, some of the alpha particles went straight through, while some deflected through some angle. See, some are hitting here, some are hitting here, some are hitting here. But it was seen that most of the alpha particle were going straight. There were no deflection. Clear? So it is also written here that very few bounded back, 1 in a 20,000. Most of them goes in deflected. So this is the schematic molecular view. So that is showing that okay, how it is going. So it must be happening in this way, that most of the space inside the molecule, inside this gold foil, is vacuum, and that is the reason this alpha particles are going straight, or it is not interacting with anything. But those who are interacting, they are either deflected, or some of them are deflected by 180 degrees. So that case is very rare. Okay, in most of the cases they are getting deflected, but not fully deflected. So three observations are there. First of all, most of the alpha rays that we have passed are passing straight. Some of them, that is 1 in a 20,000, are getting deflected, and very few of them were deflected in just the opposite direction from which they came. Okay, clear? So most of the, and what is the conclusion of this? So what is the conclusion of this? That most of them are going deflected. So this says that okay, that most of the space inside an atom is empty, or it is vacant, right? So that is the reason the gamma rays are going straight and they are moving further. Now, if you remember that gamma rays are positively charged, so if they are deflected, then they must be getting deflected from positive charge only. They must be getting you can say electrostatic repulsion, and they were getting deflected. Clear? Now, this means that the positive charge is present in a very small space, right? That is the reason that only few of them were deflected back. Clear? So that thing is called as nucleus. So that thing we termed as nucleus, in which most of the positive charge is retained. Now, if you talk about electrons, then they must be present outside the nucleus. So that is the reason they were not getting, you can say, deflected and all. So the theory that we said earlier, that okay, that positive charge is spread throughout the atom, that was completely wrong. If that was the case, then our most of the alpha particle would have deflected back, because we have positive charge. Okay, but since only few of them are deflecting, very few of them, it means that positive charge is there in a very small space. Clear? So this was all about the Rutherford nuclear model of atom. So we will talk about more. So we'll talk about it more. So first of all, one conclusion is clear, that okay, most of the positive charge is just concentrated in the middle, and most of the mass is also concentrated in the middle in a small thing, and we term that as nucleus, and electrons are just around this nucleus, moving around this nucleus, and that is the nuclear Rutherford model, that okay, electrons are revolving around the nucleus, and nucleus is present at the center. Clear? Now we'll talk about something that is very important related to your exam: atomic number and mass number. Now, first of all, atomic number. So what is atomic number? It is the number of proton that is present in the nucleus. Now this definition is very 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 important because most of the students makes mistake that they say that number of electrons. You can't say number of electrons because if you have a ion, suppose you have removed electron from it, that doesn't mean that your atomic number will change, because atomic number is what? Atomic number is basically fundamental of proton and not for electron. Clear? So this is very important, that okay, we cannot just tell that okay, the number of electron is your atomic number. It will be always the number of proton. Clear? Next is this is the atomic number. Next we'll talk about mass number. So if you talk about some examples, hydrogen has an atomic number of 1, we know, because it has 1 proton. Sodium has an atomic number of 11 because it has 11 protons. Now this atomic number is denoted by this letter Z. Okay, this is denoted by this letter Z. Now to maintain if you talk about a neutral atom, so if you have to maintain the electrical neutrality, then the number of electron is the number of protons. So in a neutral molecule, you can say that okay, we have the number of the number of electron as the atomic number, but that is not always the case because number of proton is the most basic one. We cannot just take out proton very easily. So therefore, we define the atomic number as number of proton. The same thing written here, Z is equals to number of proton is equals to number of electron in a neutral atom. Now, next thing is the mass of the nucleus, that is due to protons and neutrons, which are collectively known as nucleons, is known as the mass number. Okay, so here we take the relative mass, not the actual mass. Here we take the relative mass, and we can say in a way that the mass of the relative mass of the proton and neutron, the relative total mass of the proton and neutron, is called as the mass number. Okay, clear? And for one proton, the relative mass is taken as one unit, and for one neutron also the relative mass is taken as 1 unit. So if there are, suppose, 2 neutrons and 2 protons, therefore the mass number will be 4 simply. 2 plus 2, 4. We will take, for each of the proton and neutron, we will take the mass as 1 unit. Clear? Okay. Now, next, this is the representation that we have. Here X is what? X is our element that we are talking about. Z is the number of protons that are present in that X atom. A is the total number of proton plus neutron that is present in the X atom. Clear? Next is isobar. So these are very important. Isobar, isotopes. Now we'll talk about some stuff that is related to that is very significant for an exam. So first of all, isobars. So if you talk about isobars, so isobars are basically those elements which are having the same mass number but different atomic number. Okay, means their number of neutrons plus proton is same, but their number of protons is not same. So that is the thing. So what are isobars? Isobars are those elements which have the same mass number but different atomic number. Next is isotope. So isotope is what? Isotope are basically the two same elements which are having different atomic number. So that is the very definition, or you can say in a more technical way that which have the same atomic number but different mass number. They are known as the isotope. So their physical properties will be almost same. Suppose we have C12 and C14. So the atomic number is of course 6 for both of them, but their mass number is first for C12 is 12 and C14 is 14. Okay. So here is an example of that, or one more example of that, that hydrogen. If you talk about hydrogen, then most of the hydrogen is protium, which is having 99.985% of the hydrogen atom that is present. Now in the remaining, we have deuterium and tritium. So protium has one proton, okay, one proton and no neutron. Deuterium has 1 proton and 1 neutron, so it has a mass number of 2, and tritium has a one proton and 2 neutron, so mass number of 3. But they're very rare. Most of them are found as protium. Clear? Other example of isotopes are carbon containing 6, 7, and 8 neutrons. So if it has 6 neutrons, then it will have a mass number of 12 because its proton number is always fixed. That is 6, 6 plus 6, 12, then 13, then 14. Matlab C12, C13, and C14 are the three isotopes of carbon. Clear? Similarly, chlorine can have 18 and 20 neutrons besides 17 protons. Means 17 plus 20 it will have 37 as a mass number. And second one will have, if you just add this 7, 8, 15 and 1, 1, 3, 35. Okay, 35 and 37. So 35 chlorine and 37 chlorine. These are the two isotopes of chlorine. Okay, now this is worth mentioning. This is very important that isotopes are having same chemical properties because chemical properties are controlled by electrons and electrons are same. That is for the reason they have the same chemical properties. Okay, their physical properties can change because they are a greater mass number, so density and all can change. Therefore, all isotopes of element show the same chemical behavior. Now we have some questions here. First question, we have to calculate the number of proton, neutron, and electron in this compound. So this is the representation that we already see. X, here is the bromine. A and Z are present here. Clear? So whatever be the value of your Z will be your atomic number, will be your number of proton, and will be your number of electron because it is a neutral atom. So 35 is given as the atomic number. So Z is equals to 35, means proton is equals to 35 and electron is equals to 35. Now this is the mass number. Now mass number contains the number of proton plus number of neutron, or the relative mass of proton plus the relative mass of neutron. So number of proton is 35, of course we know. So 80 minus 35 will give you the number of neutron. That will be, so 35 minus 80 will be how much? It will be 45. Clear? Okay. So here is the answer. So 35 is Z and atomic number is 80. So number of proton electron is 35 and number of neutron is 45. Clear? Next question. The number of electron, proton and neutron in a species is equals to 18, 16, 16. Assign the proper symbol to the species. So first of all, the atomic number is 16. Okay, because number of proton is 16 here. Okay, but the number of electron is 18. Means it is having say it is having extra electrons. It is negatively charged, right? Further, the number of neutron is 16. Therefore, the mass number will be 32. So this seems to be which element? This seems to be sulfur, which is having 2 extra electron, that is 2 negative. So this will be the representation. Okay. So number of atomic mass number is 16 plus 16, 32, and the charge is 2 negative. So it is written here 2 negative. And of course, if it has atomic number of 16, it is sulfur. So 32, 16, S2 minus. So this is the overall representation. Okay. So before using this notation, we should be sure that okay, this one must be the neutral atom. Now, if it is a neutral atom, then the number of protons and the number of electrons is equals to the atomic number. If it is an ion, then we have to calculate the number of electron accordingly. And the number of neutron is always given whether the species is neutral or ion. Now, if you talk about the Rutherford model that we have seen earlier, that of course it has a nucleus in between and electron revolving all around it. The difficulty with that was that it was compared with the solar system. But if something is going acceleration, so something, if it is moving, it means that it is moving in round direction, right? It's moving in round direction means it is always changing its direction. Okay, so due to this reason, we can say that velocity is always changing. Okay, so this is very basic to physics. So we know that if something is moving in a round circle, if it is not moving in a straight line, then although its speed will be same, but its velocity will change due to the change in direction, because velocity is a vector quantity, right? So it is changing its direction and it is accelerating. Now, if something is accelerating, means it is using some energy inside it. So then and then only it will accelerate. Acceleration means it is moving faster and faster. So if you have to move faster, if it just moving in a constant speed, a constant velocity, then it is moving, right? And no external force is applied and all. But if it is changing direction, means it is accelerating. So it is kind of accelerating, and for that, some force should be needed or some energy should be required. So if in that way we think of it, then it must be continuously emitting energy, and at last it will, what will happen to that element which is continuously emitting energy? At last it will lose all of its energy and fall into the nucleus, right? Clear? So this was the drawback with the Rutherford model. So instability of atom, clear? And no distribution of energy of electron was shown. That okay, is it revolving? What is the energy and all? Nothing was discussed. So this was for today's class. With this, I end my lecture. Thank you.